second 9 weeks, first thing we did to start was talk about sequences. Remember the first day you looked at these formulas and they felt really overwhelming? Maybe they even look overwhelming now because we haven't done them in a while. Okay, do you have to have them exactly, like perfectly memorized? I mean, yes, but you probably could also have the gist of it down as long as you're able to use it. So I took a screenshot from the ones I posted on Canvas, just the summary notes. We know that arithmetic sequences relate to linear functions. Here's your formula for an arithmetic sequence. To find a future term, we need to take a term k, we don't know exactly what term that is, add the common difference, and we add it n minus k times. So we're going to do that in an example, but n minus k will always be how far apart those terms are in our sequence. Yes?
You have to memorize these, right?
Correct. No formulas are provided on the test. No trig identities, formulas of any type. Then also, but I don't know if it helps. Typically, I feel like you'd see this on a MCQ. So it's not like you're going to have to just come up with everything all yourself, right? At least you have choices to go off of. Okay, then if we have a geometric sequence, instead of having a common difference where we add or subtract, it's how we led into exponential functions in the second 9 weeks, and it has a common ratio instead. So let's practice one of each. The goal in this is to just, I went through the multiple choice, all the big ideas I saw, I tried to make sure we would do an example of each one. So it says, given the ordered pairs 3, 1 and 9, 64, determine the following. If the ordered pairs above are terms of an arithmetic sequence, determine the 13th term of the sequence. Which terms have we been given? Okay, good. The 3rd and the 9th. Just remembering the input is the term number. So 3rd number in the pattern is 1. 9th number in the pattern is 64. How do we find, this is arithmetic, how do we find a common difference?
What was the question?
How do we find a common difference?
Plug it in. You plug both points in.
So you can plug them, there's 2 ways, and y'all just said both. We can plug it all in, saying like n is usually the future term, so that would be like the a sub n would be 64, n would be 9, and we could solve for the common difference. The common difference is the rate of change. So if you want a shortcut, if you're stressed for time, you can always basically do slope formula, find the change in your outputs over the change in your inputs. So this means the pattern changed by 63 in 6 terms. And then we can reduce that, or maybe we'll have a calculator. Let's divide by 3. 21 over 2, or 10.5, either one. Okay, and then our goal is to find the 13th term. So to find a future term, pick either one. Do y'all want to use the 3rd or the 9th? 3rd, okay. So we could say I'm going to start at the 3rd term, and I'm going to add that common difference, which I could have put the number in. Oops. Sure, we'll replace it. I'm going to add 21 halves. Oops. 13 minus 3 times. I'm going to add it 10 times because these terms are 10 apart from each other in the sequence. So the 3rd term, this is the part, be careful, the 3rd term isn't 3, the 3rd term is 1. So start at 1 and add 21 halves 10 times. I'm trying to go no calculator here. I'll reduce the 10 and 2. So 20 times 500, 5 more. 1 plus 105. Okay, y'all, 106. All right, 106 would be the 13th term. If you chose to instead use the 9th term of 64, you would have gotten the same thing. I did it last class period, and we got the same number. Okay, if they tell you that it's a geometric sequence, now this is related to an exponential function, which we're going to spend the rest of the class period talking about. I put the reminder up on the board here. In exponential functions, those outputs change multiplicatively or proportionally over our equal length input value intervals if we're studying it from a table. So we're looking for a pattern involving multiplication. Here I have to use this formula. So the formula says G sub n, the nth term, came from the kth term times a ratio to the n minus k power. Okay, well, the future term that we knew was the 9th one. It came from the 3rd term times the ratio to the 9 minus 3. Oops, my brain did that for me. To the 9 minus 3 power. So 64 came from, the 3rd term was 1 times the common ratio 6 times. Yeah. Ooh, yeah. Got it. Okay, and then let's solve for R. We're all stuck together. No, you're fine, you're fine. Okay, so 64 is R to the 6th. Okay, it takes 6 what's to multiply to 64? Yeah, 6 2's. If you don't remember, if the numbers are too crazy, it would be on the calculator part. I feel pretty confident. If we take an even root, though, what does that mean for the common ratio? We took the 6th root. Yeah, technically, it could be positive or negative too. We don't really know because ours started with a positive and then 6 terms later ended positive. So that means if it was a negative ratio, all the positives would have canceled out, like negative times a negative, negative times a negative. So it doesn't really matter because look at what we're trying to get to. We're trying to get to the 13th term, which is an even number of terms away. So I'm just going to go with R equals 2. We couldn't really tell unless, hang on, the multiple choice, this is the multiple choice that matches today that's on Canvas. But like here's an example problem. Here I would know the common ratio is negative for sure because the graph is going from a positive to a negative to a positive to a negative value. And so I would know to look for a common ratio with a negative value. But without that information, we don't know. So we're going positive. Let's find that 13th term. This time I'm going to start with the 9th term instead of the 3rd. So this time n minus k is 13 minus 9. That helps us because we only have to raise 2 to the 4th power. So the 13th term comes from 64 is the 9th term times 2 to the 4th. 2 to the 4th is 16. Okay, I have an advantage because I've already worked it out. We could do some longer multiplication. It's not too bad. But 1,024. Yeah.
Just choose.
Yeah, on this one it wouldn't matter. If I picked negative, I would get the same answer because I ended up like raising it to an even power of 4.
If it was odd, would it be negative?
Yeah, if we had picked a negative and they were an odd distance away, it would matter.
Then what would it be?
Then it would be the opposite sign.
Oh.
But the question would have to tell us. Or the question would have to show us that it switches from positive to negative by giving us a table or a graph or stating that the ratio is less than 0.
Okay.
Okay, y'all. How about we graph some exponential functions now? So, y'all, we're going to cover every characteristic of an exponential graph in one problem. Okay, so let's hit the high points. We've got this. This was 2.3 and 2.4 of our course. We went over the properties of exponents. You've been using them since Algebra 1. If the base is the same and we're multiplying those two terms, the exponents add. If that base is raised to a power and then another power, power to a power, those exponents multiply. If we have a negative exponent, then we could rewrite it as the reciprocal of what we started with. And then if we have our base to the fractional exponent, we did this in the warm-up, it's the same as the radical that corresponds. A reminder that exponential functions always increase or always decrease, and their concavity can never change. So they don't have a point of inflection at all. It labels growth on the left. Growth has a base bigger than 1, and then of course decay has a base between 0 and 1. Exponential growth, the parent function increases at an increasing rate. But if we reflect that, we're going to see that that's not always true. An exponential graph decreases at an increasing rate. Remember, that's a little counterintuitive, but it means that as I look at each individual point along the way, if I drew a tangent line along that graph, the slopes are getting less and less negative. So it's decreasing still, but at an increasing rate. The slopes are getting bigger. And then it has the end behavior. Why is one end here approaching 0 on both of these?
It's the asymptote.
It's the asymptote. So let's add that piece of information here. Our exponential functions will always have a horizontal asymptote. The parent function has a horizontal asymptote of y equals 0. What transformation can change the horizontal asymptote?
Vertical shift.
Mm-hmm. Right, vertical shift is the only thing that can do it. So this can shift up or down, and that's it. If the graph reflects or shifts left or right or gets stretched or compressed, it doesn't change the horizontal asymptote. We just need to make sure before we say it's 0 that it didn't shift up or down. Okay, so let's do one problem that'll make us practice all these things. For the function h of x equals negative 1/2 times 4 to the x plus 2. Okay, first of all, is this growth or decay? Yeah, well, okay, what do I have to look at?
Oh, yeah.
Okay, look at the base first. Ignore the transformations, just the base. You've got it, you've got it. Oh, I almost wrote, it's okay, that's a G. Growth. Okay, I am going to suggest that we sketch it, just like tiny sketch, so that we can make sure we don't mess up on the domain, range, asymptote, or the little statement with all the blanks there. So think about these transformations. We have a negative, so a vertical reflection, and we have a 1/2. Yeah.
How do you know if it's reflected?
if it's reflected growth, if it's reflected and it's growth. So this is reflected growth.
Oh, wait, is it like the... Oh, okay.
So, yeah, I picked reflected growth for a reason here. So,
Wait, reflected growth, this means decay.
well, it means it's gonna decrease. I know this is the confusing part. The graph could decrease, but the equation still shows growth from the base.
Oh, okay. It's like the parent function without the reflection.
Right.
The growth.
Right. Yes, the parent function, it comes from a growth parent function, and then we're going to have to reflect it when we sketch it and think about it here in a second. Okay, the x plus 2, left 2. Just while we are reviewing, also remember for our vocab, your test might say horizontal translation by -2. Where instead of saying left, they're going to say the opposite sign, because you know everything with x is opposite. So. Okay, sketch. Did the horizontal asymptote change? No, it didn't shift up or down. The function did not, so no. It's okay. Some of us have had, a long day already taking an AP test. If you didn't, that's okay too. Okay, it's still at y = 0. And then we said this comes from a growth equation. So if you need to picture what would growth look like, my brain has to do that. And then I reflect it over the x-axis vertically. All the specific points here don't matter. We could plug in numbers for x if we really cared about all the specific points, but I highly doubt you're going to need to do that. What's the domain of this function? Yes, all real numbers. There we go, confidence builder. And this is always true for exponential. Okay, what's the range? Yes, -infinity, and then it's bounded by the horizontal asymptote at 0. We cannot include the 0.
We always have to say it.
Oh, good question. No, you don't have to. So, yeah.
Because I have it as...
Yeah, that would be fine. So, technically, the AP test could use any notation. They could say y less than 0. So they could use inequality. Of course, we could say all real numbers. We could say in words or interval notation. Mm-hmm.
Is this graph decreasing at a decreasing rate?
Ooh, yes. How do you know?
Oh, I didn't read that part. I was just going to ask just in case.
Okay, yeah. No, that's exactly what that's where I was going next. This function is decreasing. Well, I wasn't sure. I just wanted us to do the statement, but anyway, you got it. Decreasing at a decreasing rate because it is concave down. So as I look from left to right at each point, if I drew a tangent line representing the rate of change right at that point, it's getting more and more and more negative. So smaller, smaller, smaller. Yeah.
How does the range start at 0?
That's the horizontal asymptote. So this part up here was just the parent function. Ignore the blue. The graph is bounded here after it's reflected by the horizontal asymptote. This was just me. Sometimes it's hard for my brain to reflect growth in my head if I don't think about what growth looks like first. Okay, hey, before we answer the last one in this section, let's also do the in behavior. Oh, I don't know, that arrow, that throws me off. Let's just do. So if you have some space on the side, remember end behavior could be described by asking for the end behavior, or it could ask you for the limit as x decreases without bound. Our function name was h of x. The left side is approaching. The x's are. Yeah, the x's are approaching negative infinity on the left, and the y's are approaching,
Oh, 0.
yes, 0, horizontal asymptote.
That's what you meant.
Yeah.
That's what I meant.
And then on the right side, as x increases without bound, our function is approaching
Yeah, negative infinity.
negative infinity. Yes, good. And then, y'all, I really don't know if the next question will show up on the test or not. Oops, there we go. It asks us to rewrite h of x as an equivalent exponential equation without a horizontal translation. So now we're stating that the horizontal translation, the x plus 2, is no longer allowed. Okay, let me just write the equation first. It sounds like we're going to need some exponent rules. I know exponent rules will come up at some point on the test. Maybe in this form. Maybe on FRQ number 4, it'll ask you to use exponent rules. I don't know. So typically, we use exponent rules in order to simplify and combine two separate terms. But technically, I could use this first rule here that states if you have a common base and your exponents have addition in them, I could separate it into two of the same base and separate those exponents out. So let's do that. Let's go backwards and say the negative 1/2 is still there. And then I'm going to separate the x plus 2 into 4 to the x and 4 squared. And then I'm going to simplify what I can. Like, hey, we know 4 squared. 16, yes. Negative 1/2 times 4 to the x times 16. And then I can multiply the negative 1/2 and the 16 because they don't have an exponent with them. Okay, it did state to write it as an equivalent exponential equation, so I guess I'll write it as an equation here. Yes. The end behavior, yes. Let me zoom out a little bit. Oh, there we go. So just some takeaways here. We did the exponent rules at the end to rewrite the equation. It didn't tell you to use exponential or exponent rules, but anytime it's asking you to rewrite something in an equivalent form, there's usually some sort of property or identity you need to be thinking of that it's wanting you to use. The end behavior, one end always approaches an infinity, while the other end approaches a horizontal asymptote. I'm going to have you turn your page, and I'm going to give you about 5 minutes to try the whole back. It's another question like we did, and some residual fun, like, fun with residuals. And then we'll talk about them in about 5 minutes. Okay, yeah, let's bring it back together and check our answers. I'm actually going to scroll up to my answers here. Where are they at? Here they are. There we go. So y'all take a look at number 4. This function was actually exponential decay. The base was 1/3. That's how I knew it was decay. It was not reflected. The vertical dilation doesn't affect our range or domain or asymptote. So it's a decreasing function, but at an increasing rate since it's concave up. The concavity will never change. The fact that it's decreasing won't change because it's exponential. I went ahead and wrote the end behavior to the side just because we did on the front. I don't know, just in case you were thinking about it. Actually, hold on to it for something we're doing in a minute. You'll still return it, yeah. Okay, y'all, and then at the end, hey guys, will you give me just a couple more minutes? We're almost finished. All right, I had 1/3 to the x. I separated it, the x minus 1 into 1/3 to the -1. And then that created the reciprocal. So this is a little bit weird, right? Remember in the warm-up, we said cosine with a -1 is the inverse. Where here, this is actually not an inverse notation. This is a just negative exponent that makes the number flip. So we'll do, next time we're going to talk about inverse functions more when we talk about log, which is the inverse of exponential. But I flipped the 1/3, multiplied 2 and 3, got a 6. That's it. Finished. Okay, y'all, let's quickly look and review residuals. We've talked about them a little bit last class, but oops, wrong screen. Hang on. But let's review again really quick. I'm scrolling down. Bless you. Okay, so remember that if you're looking at a residual, you're not looking at the line of best fit. You're looking at how much error there is between your line of best fit, your regression, and the actual data. The big takeaway is that if we see a clear pattern, what does that mean? That's bad. Not appropriate. Okay, so another thing that I've had to just train my brain, when it talks about a model, the model is the regression equation that they picked. So they could refer to it as the regression, they could refer to it as the model. All right, so let's look at this problem. It says a regression equation was created for the points shown in the graph above on the left. The residual plot for this model is shown above as well. Which of the following statements about the regression model is true? So on the left, they're not showing us a regression. They are showing us actual data. Did their residual prove to be a good fit? No, the residual plot has a defined pattern. It's looking cubic. So scanning my answer choices, I can at least get it down to a 50-50 shot. A pattern means the model was not appropriate. So A and C are out of there. Now here's where our logic skills come into play. What type of data was provided to begin with? Okay, the actual data is exponential. They picked a model that gave them a bad fit. So did they pick exponential? No. Exponential would have been a good fit. So they must have picked something else. Answer choice B says quadratic, so yeah, must have been that. If they had picked exponential, then we would have had just a random little scattering of residual points, no pattern. So, let's walk through it one more time. The actual data is definitely an exponential shape. So if they had picked exponential equation, their residual plot would be good. It would be no pattern.
I thought the one on the left was. I thought it was the regression. I thought saying the regression model was exponential.
They're just saying that this is the data, and then we don't know what actual. Right.
Wow.
So the data you were given is exponential, not perfectly exponential. Okay, y'all, last summary I tried to put in here, the actual value, if you have to calculate the residual yourself, the actual value is going to be provided to you from a table or graph The predicted value comes from the regression equation or the model. And I underlined the AP to help you remember actual minus predicted. If you get a positive residual, what does it mean about our prediction? Yeah, it means it's an underestimate. So the model underestimated because the predicted was smaller than the actual amount. A negative residual means that the model overestimated. Okay, well, I know that was a lot of information that we covered, but at least it was a good, hopefully not too painful, quick overview. The multiple choice, I went ahead and posted in Canvas. The key is there too. Next class, we're going to do logs. So get excited for that.